So I propose we start. Welcome everyone to the WaterTalk. Before I introduce the speaker of today, Dr. Bernhard Becker, I would like to start off by acknowledging that I'm participating today here on traditional territory of the neutral Anishinaabe and Haudenosaunee people, and I should click on the...
Can I?
Yeah, thank you.
So there it is.
Good. So here you see the map. You can see where we're located. So we're located on the Haldeman Tract, highlighted in green. That was granted to the Six Nations in the 1800s. It's 6 miles on each side of the Grand River, as you perhaps know, and a fraction of that nowadays remains, which is the Six Nations Reserve. So the University of Waterloo, the Water Institute that I represent, we work on the Truth and Reconciliation recommendations, and our work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within our Indigenous Initiatives Office. So with this acknowledgement, I'm very happy to introduce the speaker of today.
Next slide.
Yeah, next slide,
Okay,
please.
so that's fine.
A guest of Professor Ponu Kumaraswamy from Systems Design Engineering. He's not a fellow countryman, but he comes from a country, or he lives and works in a country where I originally come from, in a very big water institute called Deltares. It's one of the largest, maybe the largest water research center in the world. We've had people from Switzerland in Europe here, for example, as well, from EWAC, which is another big European research center, where around 400 people work. There are twice as many people, I believe, in Deltares. So Dr. Bernhard Becker is a senior researcher and advisor there. And he's also affiliated with the Aachen University in Germany, not very far from the Netherlands. I have a very short speaker bio sketch for you. Dr. Becker holds a PhD degree in civil engineering from Aachen University, where he also still affiliated, and he has more than 13 years of experience working at Deltares, where he is, as I said, a senior advisor and researcher and a hydro modeling expert. I think Professor Dr. Decker will talk a little bit more about Deltares in his presentation. He specializes in integrated modeling in the widest sense. In development projects for Deltares, he connects software developers and software users. For water-related studies, he models interaction processes of different domains by model coupling. For cross-border initiatives, he brings people from different countries and institutions together. And as an example, he has organized a symposium of the hydrological modeling of the Meuse Basin. And I wasn't sure if that is an event that happens every year or if it was a one-off event. But it's an event where water-related researchers and practitioners from all riparian states of the Meuse Basin that originates isn't it in France?
yeah,
And goes through Belgium.
Spring is in France, Belgium, that's Wallonia and Flanders, and then the Netherlands, and there are also tributaries in Luxembourg and Germany, so many countries. Yeah, and this symposium is the 9th edition this year, so 10th anniversary. Good. So.
And you bring practitioners from all these riparian states together with the researchers, with the academic researchers to exchange knowledge on hydrological modeling of the Meuse catchment on a scientific basis. So without further ado, I'm very happy to hand over the floor to Bernhard, and I hope you enjoy this first Water Talk of the new term. Thank you.
Thank you very much for this kind introduction. Yeah. Title of my talk is not the Meuse, but it's optimization methods in operational water management. And I would like to share some advances from our side, from a perspective from the Netherlands. But here you see a windmill. I think the Netherlands is very famous for windmills. Most of the windmills, you can see water here. They are not for grain, but they were constructed to drive pumps to drain the water. outline of the talk, a few words about Deltares, and then decision support for operational water management. Very briefly, the basics of optimization in operational water management. And then I have a few examples for reservoir optimization and goal programming, and also hydrological uncertainty, the ensemble optimization, and last item, nonlinear optimization for hydropower scheduling. And this is maybe the opposite of pump operations. There, hydropower produces power and pumps consumes power, but it's a similar optimization problem. Okay, a few words or a few slides about Deltares. Deltares is an independent institute for applied research in water and subsurface in the Netherlands. Here another photograph of windmills to drain the country. It's a lowland country. Large area is below sea level. We must get rid of the water, and this is with the help of pumps, historic pumps shown here. So then energy efficiency is an important aspect, and their optimization comes in. Floods risk is always present, and we also carry out field experiments and monitoring of dikes. Here a picture from a dike failure test. So this is the experiment, so it's you see a lot of measurement equipment. Deltares has 877 employees, full-time employees, it's a bit less. 1/3 female, 2/3 male, and 39 nationalities work at Deltares. The most from the Netherlands. I belong to the group of Europe. I'm originally from Germany, and quite a high educational level, I would say. Yeah, it's a research institute. Here an image from our hydraulic lab. So I think we can say this is the hydraulic lab of the Netherlands, the largest there. Here you see a scale model of a lock to be constructed, IJmuiden lock with a ship. This kind of experiments, how does the water flow into the lock chamber and back, these are typical questions we address in the hydraulic lab. We are very proud of the Delta flume. This is not the largest flume, experimental flume of the world, but the one that produces the highest artificial waves in the world. And here you see the wave, and the question here is what the effect of plants is on wave damping on coastal flood protection with plants. Maybe you have heard from Deltares about the software. We have a lot of software products for hydraulic modeling or geotechnical modeling. We develop games and apps and also decision support tools. Most of our software is open source, so we dare to share. That's our motto. And we have quite a large software community for our hydro software and geotechnical software. This is a photograph from the Delft Software Days that we host every year in autumn. So next is starting November. And one example is the Delft Fuse forecasting platform. Here you see a map with applications of Delft Fuse. Fuse's flood early warning system, originally developed for flood forecasting, but now it's also used for drought, reservoir management, hydropower, and water information, navigation, water quality, and groundwater, so a wide range of applications. And now RTC Tools, that's a very small product, but this is about optimization. This is a toolbox for real-time control and optimization of water systems, also an open source product. I will not go into details now, but next slides are related, in most cases, to RTC Tools models. Yeah, decision support for operational water management. I brought some slides from a decision support system to give an idea why we are doing this. The Netherlands is located below sea level, or most parts of the Netherlands, and this means that we have to drain the country with the help of canals and ditches. A pump station pumps the water up to canals, and from there it goes to the sea. Here the windmills, these are the historic pumps. 100 years ago, or hundreds of years ago, there were no pumps with electricity or diesel engines. It was driven with windmills. And also the dikes are very important. So we look up to the water. Usually we live, the water is above us and not below. Challenge is then that the water goes to the sea but not back. We don't want to have salt into these canals because this is also a freshwater resource. The regional water authorities are responsible for maintaining a target water level in the canals in the operation area. And this is an example from Noorderzeivest Regional Water Authority. There's a large sluice complex here to drain the water from the Lake Lauwersmeer to the sea. This can only be done by during low tide. And there are several pump stations arranged here at the major canals, and from there the water is pumped towards this reservoir. And this is quite complex management, and their operational decision support systems have been developed. Here's a simple architectural figure. The data management platform, this is the software Deltares, collects data from weather service, rainfall, temperature, wind, seawater level, here forecast data, but also observations. And then it creates boundary conditions for different hydrological or hydraulic models and also optimization model. And these models are automatically executed, and the results should support the operators with decision support for control of these structures. Here a pump station and sluice. This image screenshot to show a bit how it looks like. Here you see a rainfall forecast map. We use different forecasting products. Here another screenshot with the hydraulic model. This is a one-dimensional hydraulic model, and here with the time slider, the operator can look into the future, look at results for a future scenario, and then colors indicate if there's a bottleneck, a problem or not. And this is finally an optimization result created with RTC tools. Here you see the rainfall that is expected for the future. The vertical line is current time. Here we have the seawater level. You can see the tidal pattern. And this gray line, that's the operational range for the inland water level. And here this line, this is the inland water level. It should be within this operational range. To achieve this, the rain comes into or falls onto the land, and it must be pumped out or with the help of the lock discharge. And this is only possible if the inland water level is above the sea water level. But there are only a few time windows where this is possible. The rest of the time, here the pumps, blue and red, they must operate. And here preferably only we use gravity discharge via the sluice if possible, minimize pump costs, but preferably only during working hours. And then we have also some obligations for nature, environment, for example, to supply a discharge for a fish ladder. This to give a bit of an idea why we are using optimization techniques for water management. And water management here in the context, it's time frame of 1 or a few days in the future. So it's not the whole year round. We look very on the short-term time scale. An optimization problem, I think most of you will be familiar with that, or at least recognize it. We have an objective function. Here we put in goals, also referred to as soft constraints. Then we have inequality constraints with system limits, bounds, minimum, maximum water level or something. And the equality constraints, that's very important because here the model equations come into the optimization problem. And when we use optimization models for water management, we go for the exact optimization or the mathematical optimization in a closer sense and not the heuristic methods, because these methods can lead to a global optimum, or at least a consistent or past stable result. I will say more later. Usually they are faster than heuristic methods, but the problem is that they come with mathematical restrictions. So it must be a linear equations or convex problem and all this. Here, different optimization types. Heuristics, they don't come with a guarantee for a global optimum, and this potentially a little change in input can produce a completely different result. And this is not helpful if you repeat the optimization a few hours later with a slightly different forecast, then you would like to have consistent results. But they are less restrictive in terms of mathematics. But on the other hand, constraints cannot so easily be included. Techniques, maybe you're familiar with genetic algorithms, ant colony technique, or simulated annealing. But for operational management, we go for this because of the fast computation, consistent results, and constraints we need for Go programming. Here's an example, or next slide's example of a reservoir optimization model. Why are we doing that? Here's an example of a beaver dam. So this is not optimized, but the beaver makes a beaver dam to impound a stream to create a lake. Here's the beaver lodge, and the idea is that the entrance is always underwater. For man-made reservoirs, it's a bit similar but more complex. Hydropower production, there we want a high water level, and flood protection. It's another use case, usually in conflict with hydropower. The reservoir filling level should be as low as possible. So here we have a conflict, and that's where optimization comes in. Make best use of the storage volume and the water. There are also, here's also a list of other possible use functions. And within the optimization, we assign priorities to these use functions. And typically the priority 1 is dam safety. So the dam should not be destroyed during a flood, and flood protection. Here an example for a simple reservoir model. I took that from the HackRes PRM manual. I think it's a great example, and learned a lot from that. Here the reservoir equation, change of volume over time is inflow minus outflow. And we have here a reservoir node with an inflow at the upstream end, then a river stretch, river section with a tributary with another inflow, and then here's a city, the river city. And there we apply some minimum and maximum discharge condition. And a typical example for an optimization result, what we expect. Here I have the green line. This is the large flood wave that flows into the reservoir. And we have also a little flood peak here at the inflow from the tributary. And the optimization model now defines a release scheme that best matches to the constraints or to the operational goals that we have. Here we have a maximum volume with the volume over time. Here's the operational range. We don't meet that, but here, more important, minimum flow and maximum flow at the river city. Yeah, what happens here? The release accounts for the inflow, but also for the tributary flow, such that we don't exceed this maximum water discharge here, except this point in time. Here, the tributary flow is already higher than the maximum discharge. So there's nothing we can do about this, but the optimization model reduces the discharge to 0 such that this is minimized as good as possible. There's also anticipation on the flood peak. So immediately the optimization model starts to drain the reservoir. So we see that the volume goes down such that there's more storage as much as possible, restricted here, to catch major part of the flood wave in the reservoir so we don't exceed the maximum volume here. So that's the anticipating behavior. And then in the end, the optimization model tries to reach this operational range here, which is not possible within this short period of time. It's 2 weeks only. I think 50 days. Yeah, here's another example. This is a 5-year scenario. We have again the operational range and the river city minimum and maximum discharge. And here I have 3 optimization results with different priority settings. So this is options for conflict resolution. In the first example here, this operational range gets priority. Then we stay here within the bounds or the operational range, but we don't meet the goals here. We can also give priority, this number 2 here, for the discharge at river city. So then we don't exceed the maximum discharge, and also we have not violated the minimum condition, but then it's not possible to meet this goal. And this is the compromised solution, a bit of everything. So here we have weighting factors. Both goals have the same priority, and with the weighting factors we can tune the result a bit towards this goal or that. So here I have a bit of emphasis here on the river discharge. Yeah, we do that with the help of goal programming. We order our goals in an ordered list according to priority, shown here, flood control, priority 1. And then the idea is that we sequentially optimize for one priority after another. And for each priority, so each line here, the results or the constraints or the goal is then applied as a hard constraint for the next one. So this ensures that we don't worse off for goals that we previously optimized for. And we still have a feasible optimization problem. What we want achieved is possible in the system, and it should not be worsened off. And we can also combine that with the weighting factors, Pareto optimization. This is the third example from the previous slide. Here I have assigned weighting factor of 0.1 for the boating range and a bit more emphasis on the flow range for the river city. Yeah, how did this solution develop? Here we see 3 results for the sequential optimization for priority 2, 3, and 9. First, we only have the operational range as a goal, so the volume is within this range, but this river city discharge is not taken care of. But for the next priority, next optimization, you can see here the gray line is the previous result, so this one, and the result here, the discharge is a bit closer to the operational range, but it's not meeting it fully. But this brings the volume more to the limits, upper and lower range. And the third one here, there's no change on the first 2 goals, but the discharge through the spillway is now shifted to the turbine. So that's the change here. No spillway flow, everything is guided to the turbine. So much. This is that was about goal programming. We have found that this is very helpful to explain results in practical applications, to understand, that many operators have clear priorities for their operational goals. So that's really a helpful approach. Hydrological uncertainty, ensemble optimization, that's something we have not applied so much in practice, only 1 or 2 cases. So I'm also curious what you think of this approach, if it's useful for your applications, or maybe it's already covered with stochastic optimization. Yeah, we found also that it's very difficult to explain what the added value is. Here's another example. We have, again, a single reservoir somewhere in Norway, and an info forecast ensemble. Weather services produce not one weather forecast, but maybe 50, all usually with the same probability. So this is basically 50 possible futures. Here I have only 5 to make it a bit easier to understand, and it's not from a weather forecast, but from historic data, but it doesn't matter so much. We don't know which ensemble member it will be. This is the inflow over time, so here's a bit floods, and this red line here, no flood at all, but 4 out of 5 ensemble members have a flood scenario. And also, again, operational range, minimum flow, and minimize flow goal to keep as much water in the reservoir, guide the release through the turbines with minimized Q spill and smooth operations, minimize Q turbine. This is the model schematization, reservoir here, inflow, and we only look at the outflow this time. Yeah, what can we do with this ensemble forecast? Straightforward idea is just to optimize for each ensemble member individually. So this is the standard optimization, and then we get 5 different, in this case, 4 different release schemes. This is release over time. And each ensemble member produces a different volume in the reservoir. So we start here and then filled up the reservoir up to the maximum by the end of the simulation period. The problem here, this is perfect schedule or release scheme, but the operator still must decide which release scheme to follow. So it's not really a decision support, it more illustrates what the future can bring. And then an idea is to optimize a release scheme that fits to all different ensemble members. And then we have one release scheme here that fits all. The problem here is that it's rather conservative, and for this red line here, the ensemble member number 1, it even means a drawdown of the reservoir volume. So if the flood wave does not come, then we lose water. So that's why I said rather conservative. And then some years ago at TU Delft, this tree-based optimization was developed with the idea to make better use of the ensemble forecasts. And the idea is to introduce branching points. Here at time step 7, there's a decision point, and similar ensembles are then grouped together, and we start with all ensemble members at once, and at time step 7, 2 of them branch upwards and 3 come to this release scheme. And the idea is that we don't find an optimal release scheme for each ensemble member, but for each branch. So then there's at least for the near future a clear decision support how to operate, and then maybe there's a new forecast available, we can decide again. Here's the corresponding volume over time. But let's look for other options when we have not only one but multiple. Here in this case 3 branching points. Then here all start with a discharge of 10, and then the 2 most extreme ensemble members, they branch off, and then there's another branching point, and only one, number 3, asks to increase the release again. And for those who have just a little inflow, the discharge remains very low, so the risk of losing water is not so high anymore. Here is another example. The decision point is at the first time step, so immediately the operator must make a decision, follow this path or that one. Yeah, this is still something to deal with, and yeah, it depends on risk assessment. So for example, if there's very flood damage expected downstream, then the operator could rather go for this path. And if the flood risk is low, then maybe can afford to follow this path. Here, 2 out of 5 ensembles point towards flood, and the other 3 not. So this is at least something to base a decision on. Here's a summary of indicators for the different methods. For each ensemble member here, 1, 2, 3, 4, 5, I've computed the accumulated release here and the maximum release on this graph. A low number is good, then we don't lose much water. And here, the number 3, the most extreme one, drives the solution for the holistic optimization. So this one is the driver, and all other ensemble members get the same release scheme. But of course, the individual optimization performs best because then we have a dedicated scheme for each ensemble member. Yeah, but we already learned this is not such a really helpful decision support. But with tree-based optimization, especially if there's more than one branching point, yeah, at least for 1, 2, and 4, this is really an advantage that brings us close to the individual solution. So, yeah, this is a way to support operational decisions here in flood conditions. The last item, nonlinear optimization for hydropower scheduling. Hydropower scheduling, yeah, we have used in the previous example only this equation, that's volumes and flows only, a linear optimization model. But when hydropower comes in, power is a product of head difference and turbine flow and the efficiency, which again depends on head difference and turbine flow, but here assumed to be constant. So this is non-convex and consequently non-linear. And this is not easy to optimize to a global optimum with mathematical optimization. What we can do, or what typical approaches are to linearize the problem. First idea, a linear approximation, compute linear, although the equation is not linear. Typically, the head difference is then assumed to be constant. That's a very common approach, but then we have a constant head difference. Piecewise linear, then we split, here this is an example for the pool elevation over storage volume, another source of nonlinearity. It's a bit easier to explain. So this blue line is the elevation storage curve that we want to apply, and the linear approximation could be this. And piecewise linear, the red line, then we split it into linear domains. So then we have a more accurate representation of the equation, but we must tell the optimization model which of the domain to use, and this adds Boolean logic to the optimization, which makes it a bit more complex. And now we have developed the homotopy method. The green line, the idea is that we can really use the desired equation, and we split the equation into two parts, a linear part and a nonlinear part, with the help of this theta. Theta takes values from 0 to 1, and we increase it gradually in a kind of iteration throughout the optimization. And if theta is 0, then only the linear part is present, and here this is treated as a constant value. And when theta is 1, this part is then 0, and we have the desired power equation with turbine flow and a nonlinear or a dynamic head difference. Yeah, so that's the basic idea. And here's an example model. Now we have 3 reservoirs and a huge list of operational goals, but for us here, most important is this one. It's a load request goal. So we don't want to maximize the power output, that's a different story, but meet a certain power generation to load balance. So load is the energy demand, and we want to meet that with our 3 reservoirs. So here are results from the 3 different approaches: homotopy, the piecewise linear, and the linear result. What we see here with the black dashed line is the energy demand, the generation request, and there's a day-night pattern for the energy demand. And the homotopy method meets exactly this demand. For the other 2 methods, we have here a deviation. So the problem is that the optimization model thinks that it's perfectly on track for the generation request, but we have a constant head difference. But the head difference is dynamic. And we have recalculated the head difference and the power output with the optimization result. And this explains why we have here a deviation in the 2 linearization approaches. And I think, with this graph, there's also nice behavior here for the homotopy method. This is the head difference over time. And here the head difference changes. It goes down because we release water from the reservoir. So this changes the water level, and the head difference decreases. And the homotopy method is then the method that can compensate that with releasing more, such that we have here a horizontal power output. While, for those methods that have a constant head difference, we end up with a decreasing power output here. So the problem here is the homotopy method does not come with a global optimum. It just has a path-stable solution connected to a linear problem. So it's not really a global optimum, but it comes with more accuracy. So that's a trade-off to make. We can optimize linear models to a global optimum, but then we lose some inaccuracy. So this is a trade-off to be made, but I think it could be at least interesting approach for hydropower optimization for load balance. I think that was the last slide. Thank you very much for your attention. If there are questions,
Thank you very much. We have time for questions. Anyone wants to kick off? I can start. This is very nice. Thank you so much for this overview. I never realized that in hydrological modeling you actually did optimization as well. I thought it was just economists that do the optimization. So this was very interesting to see. My question is this. So the country where you work and live has this prioritization scheme when there is water scarcity, when there are water shortages, when there is a drought. The prioritization, it's called the verdringingsreeks in Dutch. And the prioritization seems to be fixed. I haven't really looked at it again very recently, but I was just wondering whether some of the models that you're developing and that you're using, whether the Dutch government is actually using them in this verdringingsreek. It's part of the water law in the Netherlands, how the prioritization is set. But there's always been a bit of discussion about the efficiency of that prioritization.
For optimization models, these are usually a bit local optimization for a certain canal with some connected canals. There are priorities, but usually this is not this verdringingsreeks. We have also developed an optimization model with the same technique for the water distribution in the Netherlands. And this is really designed for water scarcity situations. And there we apply the verdringingsreeks, this priority list, to allocate water to different resources. But this is not really operational, an operational model for the short-term timescale. It's still used more as a design tool for what can happen under climate change scenarios. Will we run into water scarcity that we cannot meet the water use functions? But there, this list of priorities for different water uses is implemented as according to the law. So,
thank you. Others?
Okay, since there are not too many questions, I hope I have enough time to ask one or two questions. Just for clarification, the last part where you showed the results with the homotopy does not include the ensemble, right?
No, this is a
separate
different topic. We have the problem is ensemble. We have not proven that ensemble optimization goes with homotopy. And we are quite sure that in the current state this will not work, so we have to develop that further. Because of this connection to the connected linear problem, that's two things that are still in conflict with each other. So at the moment we cannot do both at the same time.
Okay. So just going back to the ensemble-based, So that you're doing only linear optimization, you're saying?
Yeah.
Okay.
This is just a linear model. Yeah.
So did you compare with something like two-stage stochastic optimization?
No, we didn't. I'm not very familiar with stochastic optimization, so I think this is something to do for us to connect that to the stochastic optimization. Here the driver was more the availability of ensemble forecasts. It is just there. Weather services provide that, and the hydrologists and flood forecasters, they just use it. If we have a flood forecasting for the Muse, for example, there's nothing to optimize. It's just present the possible floods extent. So that's very common. And then we said, okay, can we make use of this for water boards, water authorities to optimize the pump scheme? So that's maybe a different history or starting point than the stochastic optimization, where also price signals somehow are included. Here, this is more or less only the boundary conditions that we address, so there's no stochastic element in the optimization. So, yeah, we still have to connect that to the research of stochastic optimization. Maybe we can continue the discussion a bit more concrete.
Yeah, so
that
that's good. I mean, again, for the rest of the people, I mean, I know what you have come here for. So I wonder if you can give, because of the local interest, can you say a little bit about your current work with the Niagara Falls?
Yeah, I think so.
Just
yeah,
for because people here are more familiar with Niagara Falls than whatever you had there.
Yeah, it's so maybe I bring back this windmill. Maybe go more to hydropower. So the Niagara Falls, there's one important constraint. That's the tourist flow, to ensure that there's enough water flowing over the falls during daylight hours, and the rest of the water can be used for hydropower production. There's a tunnel for United States and for Canadian hydropower production. Yeah, and the question that we want to address with optimization models is, the scheduling. When can we use water? How can we use it in the best way? And there are some challenges. So we have the important constraint of the falls flow, but also the Grass Island pool. There's a dam, but it closes only half of the river. So if we dam up the water, then there's loss of water flowing around the dam, and this to be balanced with the additional gain of water through the tunnels. So that's optimization challenge, basically. And in addition to that, there are multiple generating units. So which unit best to use? And there's also a pump generation facility. So we could also use this to store water when the energy demand during daylight hours is high. But then there's also much water used for the falls flow. So these are challenges that we can address with optimization models.
And again, in this problem, the objective is going to be use forecast, time series forecast of, I don't know, is it hours, a day, what day ahead?
Yeah, typical use case is the day ahead schedule. So then we have hourly time steps and 24 hours. But there's also the idea to use that for a longer time frame, 15 days, so a short term, or even a seasonal forecast, and also some historic analysis of historic cases. And we will also make simulation models, for example, for such a recalculation or to refine the optimization results. Because we have mathematical restrictions, we cannot put everything into the optimization model.
Thank you.
Other?
Thank you for the talk. So this is an uninformed question, but are you or others using AI techniques in optimization modeling and or decision support systems, or do you ever see the application of machine learning in future
Yeah,
Or-
that's interesting discussion. We are discussing internally also. Yeah, this is what I've presented here as physics-based model. So what we find important here is that the water balance is closed and that we have good representation of the physical equations. But we think that artificial intelligence could be very helpful, for example, to make a forecast of the load of the demand, the power generation demand, because there are other factors than only physics play a role. For example, if the day and night pattern, and there may be events like holiday where people use more or less energy. This is something we cannot put in physical modeling. On the other hand, the water flow equations, this is still valid. So I think a hybrid approach would be good, but we have no plans to include artificial intelligence into our optimization software. Also, there are some ideas to look at connection between hydrological forecast and alternative energy production. So if there's sun and less water, this could be maybe linked together to form a better inflow forecast. So there, I think, is huge potential, but also other techniques. So this, so far, our ideas, but we are still developing, and maybe in the future I will have news to tell, maybe also something to discuss. We're looking for inspiration also.
Hi, thank you. Thank you for the talk. It's very nice to see optimization techniques being applied in hydrological modeling this way. So, from the technical point of view, you mentioned you use model predictive control for the optimization. So this is built in the RTC tools?
Yeah. What is model predictive control? It's also maybe something for me as a water engineer different than for industrial applications. I think for us the most important aspect is the moving horizon. So I can maybe show here some. This is an example. Here you see different optimization results with 5 time steps, and the first time step is used as an initial condition for the next optimization, and we move from one time step to another, and this is how the optimization develops. In principle, this is not a feature of RTC tools. We just connect different optimizations and conditions. But model predictive control is basically done with this shell of Delft views around. So the operators, they get fresh data every morning, 8 o'clock. Then an optimization run is carried out. Then they decide on operations. And a few hours later or half a day later, we used to start with 1 forecast a day, but now we are sometimes in 50 minutes intervals. But then with new data, a new optimization run is made. But this is not basically a feature of RTC tools, but I can also mimic that with a closed loop. It's a Python code, so I've also carried out some closed loop experiments. This is one example.
I see. So in the first example about the drainage problem, right?
Yeah.
So you mentioned about model predictive control, and the model is described by the Saint-Venant equation?
Yeah.
Is that correct?
I think
you mentioned it's a full Saint-Venant equation. So this is a 2D equation, right?
It's 1D.
Oh, it's 1D.
1D.
Okay. So that's feasible to solve it.
Yeah, and here's no optimization involved. Here is no optimization involved in this SOBEC model. This is just feedback control.
Okay, so you don't apply model predictive control here?
If optimization is an element of model predictive control, then it's not model predictive control. But with this one, it is model predictive control, because here an optimization model is used.
Okay, so I thought model predictive control was giving the feedback controller. So in the previous slide, how do you construct the feedback control?
Yeah, these are operational rules. For flood, it's sometimes very easy if too much water, switch on the pumps. If then else logic.
Some logic.
Yeah, but the basic idea is we can start with a hydrological model. This gives us the load on the system in terms of rainfall, how much water we must drain. Then we feed that into an optimization model, and this creates a pumping scheme, but on a very coarse operational model. And then we feed this pumping scheme, so that's discharge over time, to the hydraulic model. The hydraulic model has much more details, so the optimization model is maybe one node for such a canal, and here we have a node every 100 meters, so we can really model the water level. So then the optimization result is applied here as a time series for pump operations, and then we verify basically the optimization result with such a hydraulic model. So I believe that the simulation models and the optimization models somehow can be very different flavors, but it's very important to have both together. And with this simulation model, we can verify if this optimized scheme really works, and then the operator can adjust. I think we need a bit more pumping or a bit longer, which is not covered in the optimization model.
All right, thank you.
Thank you for the talk. Are there optimization techniques that either are specific to these problems or are perhaps more general but were inspired through the physics involved in this problem?
Optimization techniques, you mean solvers or more?
Yeah, like for example, you mentioned the homotopy.
Yeah.
Is that that's the first time I've heard about it, and so I
Yeah.
was curious if there was other sort of if it was something that came from this domain, or
Yeah, I think here's some optimization types. I think we can say that linear programming and convex optimization, these are generic approaches that come with a global optimum, and non-convex optimization not, and one of these is the homotopy method, I would say. Pono, would you say, is that correct? And
no, it's not valid.
yeah.
I mean, it means that the optimality is not guaranteed to be global.
Yeah. But these are all generic optimization methods. And for our homotopy method, we have mathematical proof for the Saint-Venant equations and for the hydropower equations. And if there are other equations, this should be tested or proven. But we have done that only for these two type of equations. Maybe is that an answer to your question? And it also does not go with mixed integer programming, where we have if-then-else logic, Booleans. We cannot use the homotopy method for this too. So it's also coming with mathematical restrictions. And it is indeed, our colleagues with operations research background, they sometimes say it's maybe not really a mathematical optimization, because we have a seeding with this linear part, so it's still in discussion, I would say.
Thank you, Bernhard. Any other questions? Last one before we close.
One last question is, again, a more practical question for some of our students here. Can you say anything about the forecasting? Do you use the specific types of forecasting time series models like ARIMA and other things?
I'm afraid not.
So it's not specific to, like...
I have a lot of colleagues that could answer this question, but I can't.
So they didn't come up with their flavor that they like?
Yeah, so ARMA is one model. I don't know where we are using that, but typically we have hydrological models. We have also our own software WFlow that translates weather rainfall into a discharge. So this is also physics-based modeling. But I've heard that for regional water authorities, the Nordoseifest example, for example, that there's also artificial intelligence AI techniques that locally produce much better results than the physics-based model. So also here, as I said, the hybrid approach is maybe the way to go, and maybe compare different models. But I have not a clear preference, or we cannot say we always use this. It depends also on what the clients already have and what fits to local conditions.
Okay, thank you.
Thanks, Bruno. No more? Everyone happy? Thank you so much, Bernhard. Let's give him another round of applause.
Thank you.
Thank you for coming here. Thank you for attending.
Yeah.